going to give a shot at implementing a linked list, and I'm going to do this entirely unrehearsed. We're just going to, kind of give it a go and see how that works. So that's fine. I don't care about that. Okay. So we're going to make our linked list. So let's make a new header file. Let's just make a new source file pair. New class. This is going to be our list. And we'll add it to both build targets. Add. Okay. And I actually prefer the pragma once style. Now we need to put this in a namespace so that we don't clutter things up. What are we going to call this? Let's just call this GCU. Okay. What's the name of our class? Like CSET? CST. Now let's call it CST. So we're going to have this little list object. Now, we need some public elements. I don't think we need anything here. So let's just pick the default. So far, we will use a default constructor, and default copy constructor list const reference right hand side. Sometimes people call this other, and we'll make that default too. So that's our copy constructor, isn't it? C++ copy. Yeah, of course, because it's a constructor, so it doesn't have a return type. Okay, so those are kind of the law of three, and we're just going to follow the defaults for now. If you didn't do this, this is what you would get by default, but I just decided to explicitly call out the three core kind of pieces in C++. There's also the move constructor. You can read about those. We're not going to get into move semantics right now. Okay. We're going to need some pieces. So let's see. We're going to have a node. And a node will be and let's not use a raw pointer. Let's use our unique pointers. Okay. When do you use unique and when do you use shared pointer? Unique is an owning pointer. It owns the thing it points to. Shared pointer is a little bit heavier weight, so prefer unique pointer until it doesn't fit, and then try shared pointer. When do you use a raw pointer? A raw pointer is the modern C++ way of looking at raw pointers now is they are non-owning pointers. So they don't own the thing they point to. So Rust actually codifies this concept of ownership in what they call the borrow checker. C++, it's emerging as a paradigm or a set of conventions on which pointer types you use to define ownership. Okay, the GSL, let's see if we can find that up. GSL C++. This is the guidelines support library. This is a fantastic set of resources resources and rules on what it means to write meaningful, core, correct, modern C++. So this is a fantastic resource. I would recommend, picking one or two of these a month and just kind of reading through each of the little pieces and trying to understand and maybe take one or two rules and drop them into your code. These C++ core guidelines, and then the GSL that implements those guidelines. Fantastic resources. Okay. So let's define what our node is. Okay. We don't want people to use the node by default, so namespace. So there's a convention to put things in the detail namespace to hide them. And we're going to forward declare node, so we're not going to put its definition here because we don't want to leak all the details of this, but we have to make sure that we put node somewhere. So actually, this actually drives me crazy. So we have this. Okay. No template unique. Oh, because it's unique putter. Okay. Let's split this. Split vertically. And we'll put C++ over here. I just have this convention to... The code has to be on the right. I don't know why. Okay, let's replicate our namespaces. Namespace CST. Namespace detail. Class node. And we'll actually put the full definition in here. And a node has some piece of memory. So something. This is the data for the node. And a node also points to the next thing, right? So this is going to be a standard unique putter node to next. Okay, and by default we'll initialize that to null pointer. So that's our node. Let's define the pieces of our class. So we have no methods yet, and so far we're good. Let's write a test around this. See if we can instantiate one of these. Let's make a separate test file. New C++ source file. This is just for tests, so this will be list tests. Okay. Add. Let's define this guy. And we need to define this guy. This is like this will just be an API test. Create a list. So we are using namespace CST. We need to include list.h. And so let's create our list. Let's not do that right now. So we got CST list L. Can we just even make one of those? So that's our test. Build it. Okay. What's wrong here? Invalid application of size of for CST detail node. Okay, so it appears we can't forward declare this guy and use a unique pointer here. So that's too bad. Invalid application of size of, let's see, unique pointer forward declare. Forward declare with unique pointer. Let's see. I found it useful to forward declare definitions and combinations with you. It compiles and works with GCC, but the whole thing seems strange, and I wonder if this is standard behavior. Since B is a complete type when I declare a unique pointer. Alright. So what it's saying is we actually need to do this. This is build. Okay, well that's a bummer. Alright, so we'll stick with shared pointer for now. We'll refactor and come back and see if we can run, refactor this to a unique pointer later. Okay, let's create our terminal. Art and maze and and tests. Okay, so let's do test just s, and is it running all of our tests? Test. Where's our new test? Test list.cpp. Did it get into the CMake lists? No, it did not add it. Okay. Tests list test CPP. Alright. Enable auto reload. Looks good. Build the sucker. Okay. Perfect. 10 assertions, 1 equals 1. Okay, we're happy. Okay, so we can construct our list. We can make one of those things. So that's awesome. So now let's think about our API. We want to be able to append to a list. And we want to be able to print out the value of a list. So we want to be able to do list.add. We want to add a 9 and an l.add a 10. And then we want to get, so let's do l.get 0 equals 9, and this one will be 10. So we kind of want that to work, right? Okay. So of course this doesn't compile, so let's go ahead and make this compile. We need a function that returns nothing, and it is an add, and it takes by reference an integer, and by constant reference, and this will be an I, and that's it. Okay, so we got that guy, and then we need to be able to get things. This is going to return an int, and we're going to get it, and this takes nothing. And actually this is const. It will not change the state of the function, so we can label that as const. So get itself will not change anything, but it does take an index, so const reference index. Now this is just a habit I have. Int and pointer are probably the same size, so this is not an efficiency gain, and the compiler will probably elide this and remove it, but this is a really good habit to get into. Just always pass things by constant reference, or as they say, by reference to const. So by saying it that way, it reminds you that you're actually, the const goes on the right side of that ampersand, the left side of that ampersand. Okay, so let's compile this and watch our tests fail. Okay, undefined reference, yeah, so we defined the prototype for these methods, but we didn't actually declare them. So let's go declare them now. Okay. So outside the detail namespace, okay, this is going to be our list method, and this is going to be our list method, and we're going to give this implementation, and we're going to give this implementation. And for now, we're just going to return 0 and see if it compiles. And we'll run our tests, and of course one failed. So which one failed? It's our method over there. Okay, cool. So our tests failed. And that's what we want. This is called red-green refactor. Our test is currently red, so let's go make it green. So if we want to add something to this list, then we're going to need to instantiate. Let's go look at the definition of this. We're going to need to make a node. So this will be auto n equals standard make unique UNIQUB. Alright, and let's just say that you always have to pass in data to a node. So then this would be, we need to be able to set that data. So set data int I, data equals I. This returns nothing. And then void set next. This will be a standard unique pointer said, we're not going to get into move semantics right now, so we'll just use shared pointer. Doing shared doesn't do anything, so we have no shared pointer node. So that's going to be our next thing. We're going to do n.setDatum. N points to set datum. I. N points to set next. And this will just be node pointer. It will actually do that by default, so we don't need to worry about that. Let's compile this, see how happy it is. Okay, let's run our tests, see if it explodes. Okay, it explodes. Segmentation violation signal on line 13. So that's this line here. On this tests 13. Okay, so this function threw segmentation fault. Shared pointer set datum n dot set datum I think it's this one. So let's make that null pointer. If n, let's just call this head. So if head is a null pointer, then we're actually empty. We are empty. And we need to navigate to the next one. And then we'll do head dot then we'll do list this set next head equals n. Okay. Let's see what this does. This is probably still going to seg fault, and we'll take it from there. Okay, great. So our seg fault's gone. So we got rid of that null pointer exception. Our test is still failing, but our nasty little seg fault right there, it's gone. So that's good. Okay. Now let's seg fault came back. So if head equals null, let's figure out where this is. Head in. Okay, this is what it was supposed to be. So that took longer than I expected to debug. Welcome to C++ sometimes. Now, we should actually be able to get the first thing. So, if idx equals 0, then we just want head, so we're going to return head dot, oh, we actually need to get the data. So, we don't really need, because this is totally hidden, we don't need any of the private, public stuff. We'll just make everything public. That's not a big deal. Because it is private, totally within our header, or within our source file, we'll just return the data, and that's it. That's an int. That's an int. And we'll build this. Okay. Look at our tests. Great. It actually worked. Now it's failing on the next one, the number 1. So else we need to go through the keep fetching on the next pointer until we get there. So let's take an int I equals 0 while I is less than the index plus I. And then we will do head points to next. We're going to need a pointer here. So auto p equals head. And we'll say p dot next is not equal to null pointer if p dot next is not equal to null pointer. P equals p dot next. Okay. Then we'll return p dot data. And this should actually work for the 0 case too. So we don't need this anymore, I think. We don't need this anymore. Build that. And we'll run it. 9 is not equal to 10. Okay, so I comes in, p is pointing to I is not equal to 10 because we don't set the next. Okay, so we're getting somewhere. My wife is texting me. Okay, so we're actually going along through here, and we want to traverse. So if the head's not the null pointer, then we want to continue searching for the null pointer. So we'll need a pointer, auto p equals head, and while p dot next is not equal to null pointer, p equals p dot next. Okay, and then we'll just say p dot next equals n. Okay, let's compile this. Look at our tests. Hey, they're passing! So we actually created a linked list, and we added data to it, and we can get that data back out. Okay. And now we just want to be able to print print a value of a list. So let's do I. Actually, that's it. We can print and we can get our values. We don't even need this. Okay, that's cool. All right. At this point, we have a linked list. There's our specification of the linked list, and here is the actual implementation with the add and the get function. We could go implement operators, so instead of doing this get, you could implement the operator, the array operator, so you could actually be more idiomatic of C++. But one thing I would like to demonstrate is one of the really cool things about C++, and that's generic code. So what if you wanted to make a list of characters instead of just integers? How could you do that? What if you wanted to do l.add c l.add d, and then strings, because in C++ characters actually are numbers, so that doesn't actually work, but we'll do this, strings. What if you wanted to do that? That doesn't compile. So what's it take to make that compile? Cannot convert from constant char string to int. Okay. So what we can do is we can say template type name t, and we can parameterize node on t. This then becomes a t. This becomes a t. T can be int by default. Okay. This becomes a t. This becomes a t. This becomes a t. This becomes a t. I think this is like this. Okay. Now, welcome to one of the nasty things about C++. As soon as you want to genericize or template something, all this code has to move to the header file. So this becomes that. Okay. This to there. This goes away. All this needs to move up to the header file. Actually, that might have been able to stay there. Yeah. stay there, I'm pretty sure. That way we can keep it hidden in our detail. Why does it think this is never used? P dot head, P dot next equals n. I don't know what that's upset about. Okay. Now, we come over here, and we want to make this a standard string. So now we're actually passing in the type. Get doesn't take a t, it returns a t. What happened to our... Oops. There, okay. We need this. Delete this one. And this becomes a t. And that becomes a t. And this is an int. Okay. Compile. Invalid incomplete type. Set datum. N. Okay. So then this does have to move, because it doesn't know about that method. But could we... There we go. Let's go back to our tests. Great. Now we have these things, right? So now we created our list that worked on integers, and then we parameterized it on type, so now it supports strings. Now our same code supports strings. You can make lists of whatever you want. Let's make a list of doubles. And then this becomes 3.14, and this becomes 2.71. Now, because they're doubles, you can't it's not smart to actually do equal equal, so you want to bound it. So you want to say it's either greater than or equal to 3.13, and L dot get 0 is less than or equal to 3.15. So that is when you're testing with doubles, you want to make sure that you bound it on a tolerance. You don't want to just do the exact number, because floating point values are not exact. Okay. What's this upset about? Oh, you can't actually do this in check. You need to split this up. And we're good. So that's it. That's a list. And we parameterized it on type. So you can kind of get crazy with it, or you can leave it where we left it a few minutes ago. All right. Thanks.